Okay, so let's begin. We welcome Amir Ahmadi from Princeton. So he'll talk about optimization and dynamical systems.
Thanks very much. Thank you, Alexei, for the invitation, and thank you all for coming. So this talk will have two parts. The first part is more about the use of optimization to analyze stability properties of polynomial differential equations. I'll be talking about sum of squares Lyapunov functions and analyze sort of their power and limitations. This is joint work with my graduate student Bashir al-Ghadir. The second part, which is almost completely independent, so if you don't follow all the details here, you can start fresh in the second part. Sort of the opposite is about bringing some ideas from dynamical systems to optimization. In particular, I'll talk about the new class of optimization problems we call robust to dynamics optimization. Okay. So I'm not very familiar with the background, so I think I encourage you to stop me and ask questions, especially at the beginning. And even if I don't finish all the details, that's fine. I can just make this as educational as possible. So in the first part, I'm looking at a very concrete decision question. So I have as input a polynomial vector field in n variables. So each entry of f is a multivariate polynomial. This is an example. And what I've given as input is the coefficients of these polynomials, which are rational numbers. And this vector field has an equilibrium point. I'm always going to take it to be at the origin, so f of 0 is 0. And I would like to decide one of these two properties, either local asymptotic stability or global asymptotic stability. So as a reminder, what is LAS? It roughly means that there is some neighborhood of the origin of positive radius, such that if you start the initial condition in that neighborhood, the trajectory will asymptotically flow to the origin. So that's the second property. The first property is stability in the sense of Lyapunov. It says that if you give me any epsilon ball, I should be able to find a possibly smaller delta ball, such that if I start in the smaller ball, the trajectory for all time will be in the bigger ball. And this is sort of the intuitive reason why you want this property to hold, to call a system stable, is that you don't want to have a system where trajectories flow to the origin, but before they do that, they move away by a large amount. So let's say you start here, the trajectory goes out, and after a long time comes back in. You don't want to really call that stable. So these two together are definition of local asymptotic stability. So global is the same, so it has the first property the same. The second is that no matter where you start in Rn, all trajectories in Rn flow to the origin. Okay? That's the question I'm trying to answer here. Mm-hmm. Okay, so I'm not going to spend that much time, but this property has many applications in control, so I'll show you one in robotics. So for instance, the equilibrium point could be the upright position of a robot, and you're trying to design a controller that keeps the robot stable, in the sense that if somebody pushes the robot a little bit, the controller will take the robot back to this equilibrium point, or the origin. You should think of it as exactly the top right position. Right? Or you can even think of proofs of stability as being proofs of convergence of algorithms in optimization problems. So you can think of any algorithm as being a dynamical system, or it's usually a discrete dynamical system, and the equilibrium point as being the global solution to whatever problem you're trying to solve. And you want to prove that if you start near the solution, the algorithm will actually take you to the solution. So that's another application of being able to prove stability of dynamical systems. Okay, so and as I'm sure most of you know, so the way this problem is approached, at least most of the time, is by finding a Lyapunov function. So let me remind you, so Lyapunov's theorem says that if you find a scalar valued function v, which vanishes at the origin, is positive everywhere else, and its derivative along the trajectories is negative, so this is the derivative with respect to time, which is the inner product of the gradient with the dynamics. If these inequalities are true in some neighborhood of the origin, then the system is locally asymptotically stable. Okay, and in fact, that neighborhood will be part of the sublevel set of V in that neighborhood will be part of the region of attraction. And if these inequalities hold everywhere, and V is also radially unbounded, then you have global asymptotic stability, right? And this is an if and only if. So such a function is guaranteed to exist if your system is stable. You can prove some properties of it. So for instance, you can prove that there will always be a continuously differentiable function that satisfies this. But the whole question is, how do you find this Lyapunov function? Yes?
Is there a complex version of this, complex number version?
Over the where the dynamics is also over the complex numbers. I don't know, actually. That's a good question. I would imagine that there should be. Probably by... I don't know this. I'm just thinking out loud, but probably I would try to map it to a real system in twice the dimension. We'd have to see how stability is preserved, and then transfer existence of a Lyapunov function. But I've never worked with complex dynamics.
Inequalities hold everywhere. Already of inequality.
Yes. So okay, let me be more precise. So for global, so here so these inequalities are everywhere except at the origin. That's what
except the origin.
Yes, at the origin, both v and v dot are 0, right?
Mm-hmm.
Everywhere else you want this to hold.
Okay.
If that is true, and if v on top of it is radially unbounded, which means it has compact sub-level sets, that's one characterization, then you have global asymptotic stability. For local asymptotic stability, the condition is that if these inequalities hold in any neighborhood of the origin, except at 0, because at 0 both of them are 0. Okay. Good. But our task essentially is to find this v that satisfies this, right? And the question is, okay, what class of functions do I search among? And what has been very popular since the year 2000, this is essentially when the PhD thesis of Pablo Parillo, who's now at MIT, came out, is to search for polynomial Lyapunov functions. So why? Well, two reasons. First of all, f is a polynomial itself, so it's kind of natural to look for a Lyapunov function which is polynomial. But more importantly, if you search for polynomials, then there is an optimization technique called semidefinite programming that can automate the search, the task of finding the coefficients of v such that these inequalities are satisfied. Okay. So I'm not going to tell you all the details of how this works, but maybe an idea of how it does. So the way this technique works is to give an algebraic proof of non-negativity of polynomials. So let's start with a very simple task. Suppose I hand you this polynomial in 3 variables and degree 4. And I ask you, is it non-negative? Which means, is it true that no matter what x you plug into it, you get a number more than or equal to 0? Any guesses? Okay, so this is a difficult task, as you can imagine, right? But if I take the same polynomial and I rewrite it for you like this, so this is what we call a sum of squares polynomial, or SOS for short. So a polynomial is a sum of squares if it's a sum of squares of other polynomials. Then you should be convinced immediately that this is non-negative, right? If you don't believe me, all you have to do is multiply this out and check that you get p back. And once you have that, you're convinced. Right? So it turns out two things. First of all, this extends to the constraint case. So here I wanted to prove that p is positive everywhere. You can also use a modification of this to prove that p is positive on a certain subset of Rn, as long as that subset is defined by polynomial inequalities. If you're interested, I can tell you how that works. But the second nice thing is that the way this decomposition was found is not by hand, it's completely automated. So you can solve a semidefinite program, and the solution to that will give you this SOS decomposition. Any questions? Okay. Moreover, so the way I presented it here, p was fixed. I gave you p and yes.
What do you mean by optimization here?
Okay, I'm not showing you the optimization problem. Maybe okay. So maybe I tell you on the next slide. There is some optimization problem. It is a convex optimization problem called the semidefinite program. If you solve it, it will do two things. First of all, it will tell you yes or no, is p a sum of squares? If no, then nothing. It cannot be written as a sum of squares. If yes, you can take a solution and extract from it this decomposition. Okay. Again, if these questions are more interesting, I can go on the board and explain how this is done. But
I just want to know the meaning of optimization. Are you saying that you can write it as a sum of square using the least degree, or what?
Okay, so do you have a chart?
Doesn't make any sense.
Oh, there's John here. Yeah. That's a very good question. So P of x, let's say he has n variables, and he has degree 2d. Wait, why degree 2d? Because if the degree is odd, it can never be a sum of squares. It won't even be non-negative, right? So there is a theorem that's actually quite easy to prove, which says that P is a sum of squares if and only if there exists a symmetric matrix Q of size n plus d choose d by n plus d choose d, such that the following is true, such that P of x is equal to z transpose x q z of x. I'll tell you what z is in a second. And this matrix Q is positive semidefinite, meaning it has non-negative eigenvalues. Okay, and where is z of x? So where z of x is the vector of all monomials of degree less than equal to d. Okay, so P at degree 2d, z would have all monomials you can think of degree less than d. So for instance, if the dimension is 2 and 2d is 4, z of x would be 1, x1, x2, x1, x2, x1 squared, x2 squared. These are all monomials of degree up to half the degree of p. Right? Okay. So now to your question, what optimization problem am I talking about, right? So there is something called semidefinite programming, or SDP for short. So this is an optimization problem where you want to minimize a linear function of a symmetric matrix. So the decision variables of this optimization problem are symmetric n by n matrices. Okay? Their objective, this is just some notation for denoting a linear function of the matrix. And the constraints of this optimization problem are some other affine constraints. So let's not worry about that, but the important one is that the matrix needs to be positive semidefinite. So this is what a semidefinite program is. Now, how does it connect to this? So here the optimization problem, okay, you give it P, which is the coefficients of this polynomial, right? Its task is to find Q. So the decision variable is a symmetric matrix Q. Okay? That's why it's a semi-definite program, because it needs to find a matrix which is positive semi-definite that satisfies this equation. So this inequality is for all x. So essentially it needs to match the coefficients of P with the coefficients of this polynomial. Right? And then this can say two things. Either it would say infeasible, meaning there is no Q that satisfies this equation. So then you can claim that, okay, your polynomial was not SOS. Or it would say feasible, and it returns a solution for you. Let's call it Q star. Okay. You can take Q star and from it extract this decomposition. And usually what you have to do is to factor it, say a Cholesky decomposition would do. And from that, you can write P as a sum of squares. So that's the long version of the answer. So the optimization problem is what's called a semi-definite program. Its task is to find this symmetric matrix Q. Okay, so let's see how this is useful for dynamical systems, because I assume that's the background of most people here. So here, just one concrete example. This is a vector field that you start with. The origin is an equilibrium point, and you want to test if it's globally stable. And this is actually can be completely automated. There are multiple software packages. One of them is called SOS Tools, which was used here. There are other ones. and then you just ask it to find for me a degree d should be fixed, degree 2 function, let's say, that is a sum of squares, and minus v dot is also sum of squares. Because if this is true, then these inequalities are true, and the system is stable. Okay. Yes, okay, good. Are you worried about the non-strict? Yes.
Should it be the other way?
No, so, okay. So if a polynomial is SOS, then it's non-negative,
okay.
but,
Okay.
so this
I thought you
v of
were-
x SOS implies v of x on negative for all x. So for a property like asymptotic stability, you need strictness, right?
I mean the v dot.
Oh, I have a minus sign. So this would imply
Yeah,
that
but
v
in
dot
the-
is less than
But in
0.
the definition, isn't it the
Less
v
than.
dot is less than 0?
Yes, but I have a minus here.
Oh, I didn't see that. Sorry.
Yeah, no worries.
Sorry.
Yeah. Okay, and let's not worry in this talk about strict versus non-strict inequalities. So just take my word that they can both be handled. Essentially, this matrix that I talked about, you need it to be positive definite instead of semi-definite. So you ask, find me a Lyapunov function of degree 2, and SOS tools will tell you there is no such Lyapunov function. And then you ask, okay, find me one of degree 4. In that case, it declares success. It outputs this Lyapunov function for you. And the way he did it was by solving in the background the semi-definite program. This is what I had on the board. So he finds these two matrices, one for v, one for minus v dot. Both of these matrices are positive definite. And that proves these inequalities. End of story, the system is globally stable. Right.
Is there always a Lyapunov function of some degree?
Okay, that's the question I want to answer in this talk. So I'm still doing it. That's great that you asked that. So the first part of the talk is about that question. Okay. But anyway, that's why there's excitement in polynomial Lyapunov functions, because we have this technology which can automate the search of finding the Lyapunov function.
So are there rational Lyapunov functions?
Rational functions,
Yeah.
ratios of polynomials?
Yeah.
I will actually address that too, to some extent. I'll tell you what we know about these questions. That will also be in the first part. Okay, so I also want to show you, this is now even more details hidden, but this stuff has actually been applied by roboticists too. And so the previous example was a global stability example. This is a local one. So here you want to prove that is there a neighborhood that the robot can handle if it deviates from this equilibrium point. And let's see if this plays. Yeah. So there was some semi-definite program solved in the background, which in this case, this is not an analysis problem, it's a control problem, meaning that the dynamical system is not given to you and just asking you, is the system stable? You can control part of the dynamics to make it stable, right? So that problem can also be handled. And you see, it's a reasonably large problem. It has 30 variables and multiple control inputs. And this semi-definite program succeeded, at least in this case, to find the region of stability and stabilize the robot. Okay, so now I want to just, to answer your questions, I want to have a more technical view on this problem and answer the question, does this always work? If a polynomial system is stable, will there always be a polynomial Lyapunov function of some degree? Or, if you're a computer scientist, you can ask even a more basic question. What is the complexity of testing asymptotic stability? What is the running time of any algorithm? Can you prove some lower bounds on it? So let's start easy. If the degree of the vector field is 1, in other words, you have a linear dynamical system, then this is the classical case. We know we can test both, well, first of all, local and global stability are the same in this case, because the system is homogeneous of degree 1. And you would have an asymptotically stable system if and only if the matrix A is Hurwitz, meaning that these eigenvalues are in the open left F-plane. And that will happen if and only if there is a quadratic Lyapunov function. So the answer to Alex's question in this case is yes. If the system is stable, there is a degree 2 Lyapunov function, always. Right? So interestingly, if you want to find this Lyapunov function, one way to do it would again be to solve a semi-definite program. You need to find this matrix that defines the quadratic form. That's again a problem of searching over matrices that satisfy positive definiteness conditions. Questions about the linear case? Okay. So now, unfortunately, the nonlinear case is a lot more difficult and a lot less is known about it. So there's a conjecture of Arnold from the 70s that says that there should be no algorithm whatsoever that can decide this property with any running time, right? So whatever your algorithm is, even if it has a triple exponential time complexity, it cannot be correct on the yes/no answer it gives to the question of stability on every vector field of, say, degree 2. Right? So this is still unknown whether this conjecture is true or not. But there, in fact, there's a connection to the question that Alexei asked. So if we could prove that asymptotically stable polynomial vector fields always admit polynomial Lyapunov functions of some degree, and if you could moreover compute a degree bound, this degree bound can be very bad, it could be towers of exponential, but if it's finite, then this conjecture would be false, because it turns out that the question of, if you fix the degree and you ask, is there a polynomial Lyapunov function of degree 100, that can be answered in finite time. There are multiple ways of doing it, for instance, by quantified elimination. So this question, therefore, connects to the question of complexity. Okay, so I want to tell you sort of partial results we have towards this question. So the first result is that testing asymptotic stability is an NP-hard problem. Okay, so I'll give you a rough proof of that. So what that rules out is not any algorithm, but it rules out any efficient algorithm unless P equals NP, right? So there cannot be a polytime algorithm. Let me give you a rough idea of this proof. So first of all, is a stronger claim. So this is true even, okay, so first of all, the claim is for cubic vector fields. And it's true even if your vector field is homogeneous. So what is a homogeneous vector field? It's a vector field where every monomial has the same degree. All the monomials have degree 3. So one property of homogeneous vector fields is that they scale. So if you look at f of a scalar times the vector x, this is lambda to the degree, in this case 3 of f of x, right? So if you scale, the vector field behaves the same way. And because of that, for homogeneous system, local and global properties are the same. So this sort of for free proves that both properties are NP-hard to test. Okay, so what's the idea? So if you've seen proofs of NP-hardness, you need to encode some previously known, typically combinatorial problem, which was known to be NP-hard into this, right? So in this case, the problem that we start with is what's called 1 in 3 3-sat. So let me remind you what that is. So in 3-sat, you have what's called a Boolean formula. So these are logical ORs, these are logical ANDs, and this bar is a negation. Your variables, in this case you have 3 of them, is a toy example. They only take 0, 1 values. So your job is to assign values 0 or 1 to each of the variables, such that what happens? So in 1 in 3 3-sat, I want in each parenthesis, so each parenthesis is called a clause, I want to make sure I have exactly 1, 1, and 2 zeros. Okay, so for instance, this example I have here is satisfiable because if I set x1 to 1, x2 to 1, x3 to 0, in every clause I get 1, 1, and 2 zeros. Does that make sense? Okay. So the answer to this instance is a yes, or this is a satisfiable instance. If I have another instance, actually I can ask you, so this is actually identically the same, except I just remove this negation from here. If you think about it a little bit, this is actually not satisfiable. So if you try even all the 8 possibilities, none of them would work. Right? So this problem is a very canonical NP-complete problem. So we don't know any algorithm for it, which is essentially better than just trying all 2 to the n possibilities. Okay. So
what is the significance of 2, 0, and 1, 1?
Okay, so good. So it will make my reduction easier. So if I didn't have that property, I would have the same theorem for vector fields of degree 5, okay, which would be a good result, but this is a better result because I'm proving that this is hard even for cubic. So the 3-sat, which is a more famous problem, not the 1 in 3 3-sat, just 3-sat, asks you to find an assignment to this Boolean formula such that the entire formula evaluates to 1, right? So in that case, you need to just satisfy these clauses with 1, 1. You don't care that you have 1, 1, and 2 zeros, right? I could have used from that, it turns out you'll see on the next slide, because of some technicalities of how you encode this into a polynomial constraint, the degree would go up. So that's just it. Right? Okay, so what is my task? My task is to design a cubic differential equation.
So
Yeah.
you're saying that the 1 in 3
Mhm.
satisfied the problem is already strongly known NP power.
Yes, that was known. So in fact, there is a reasonably straightforward reduction from 3 sat to 1 in 3 sat.
Okay.
So this was known, and I'm starting with that.
All right.
Yeah, good question. So what is my task? I need to design a cubic differential equation which is asymptotically stable if and only if this input that is not satisfiable, right? So from every input like this, I need to write down a cubic vector field such that the vector field will be stable if and only if the answer to this question was a no. Okay. So how is that done? Again, this is just a proof in one slide. So it has 2 steps. So you take this input and you write a polynomial of, in this case, degree 4, and that's the part that answers your question. If you work with 3 sat, this would have degree 6. And then, okay, so let's roughly look at this polynomial. So first of all, this polynomial is a sum of squares, so it's always non-negative. And the interesting question is whether it has a 0. So how can this have a 0? If a sum of squares is non-negative, the only way it can have 0 is that every single term is 0, right? But what happens if this first term is 0? It means each xi is either 1 or 0, right? So that's encoding the fact that this was a Boolean variable. Now, what am I doing here? This is there for each clause there is 1 term, and I'm ensuring that the sum is 1. Well, how can the sum be 1? That can only happen if in these 3 terms we have 1, 1, and 2 zeros, right? So this is why I'm subtracting -1 in every one of them, right? So that's encoding that property. So in short, this polynomial that I wrote down will have a 0 if and only if this instance is satisfiable. The next step is needed for technical reasons, but this is what we call homogenization. So you take this polynomial in n variables, you introduce just one more variable y, and this homogenizes it. So it produces a polynomial of degree 4 where every monomial has degree 4. And then finally, your vector field would be minus the gradient of that. So if this has degree 4, the gradient will have degree 3 as promised, and it will be a homogeneous vector field. And the claim is that this will be asymptotically stable if and only if this is positive definite. So the rough idea is that if this polynomial is positive, then it will serve as a Lyapunov function for this vector field. So that will give you a proof of stability for free, because there you go, that's your Lyapunov function. If it's not positive, then it will have a 0 somewhere.
So
Yeah.
so so the vector field is not given to you, but you are
Okay.
finding it.
The vector field depends on input. So you give me one of these instances, I write down the vector field for you. You change the instance, my vector field is going to change. It's going to always have degree 3, and it's going to always be homogeneous. But whether it's stable or not depends on whether this instance was satisfiable or not, right? So so what is the logic? The logic is to show that if you give me an algorithm for testing stability, I can use it to answer 1 in 3 sat.
Okay.
Because nobody can answer 1 in 3 sat, you should not be able to give me an algorithm for testing stability, right? Okay. So that's how this reduction works. So in short, this proves that unless P equals MP, there should be no efficient test of stability. Now back to Alex's question. Does stability imply existence of a polynomial Lyapunov function of some degree? So maybe this proof implies that, okay, there won't be any polynomial of low degree because that would be efficient, but maybe there is one of degree 1,000, right? So it turns out that the answer is no, but I want to distinguish whether you're talking about global stability or local, and whether you want the Lyapunov function inequalities to hold over all of Rn or near the origin. So the first version was easier, and we had an example in 2011, which is actually remarkably simple because it's almost a linear dynamics except for one term. So what is the claim? The claim is that the system is globally stable. No matter where you start, trajectories flow to the origin, but there is no polynomial Lyapunov function that can prove it of any degree. And this, I think, at the time was a bit surprising because this SOS Lyapunov functions they almost worked on most examples that people cared about. So it was very surprising that such a simple example can make it fail. So how do you prove that the system is globally stable? Well, you do it by giving a Lyapunov function. In this case, it's not a polynomial. It's one that uses the natural logarithm. But you can check that, oh, this is obviously positive everywhere. It's 0 at 0. If you take the derivative, it would be negative everywhere because it's a minus sign, sum of squares and sum of squares here. So how do you prove that there is no Lyapunov function of any degree? So that's more interesting. And what we did was that we just considered what the trajectories do in the non-negative orth end. And if you take, so first of all, let's look at this dynamical system. Y dot doesn't depend on x, it's minus y. So the solution to this is e to the minus t. So the y variable is going to go down exponentially fast to 0 on its own, right? But let's look at the x variable. So the sign of x dot depends on y. If y is more than 1, x dot is positive. So this is the y equal to 1 line. So above that, x is going to the right. As soon as y reaches 1, that sign is negative, so x changes direction and goes to 0. That's what's happening, right? But as you can see, when y is more than 1, the rate of growth to the right is much higher. So this is an exponential growth. So the trajectory is moving to the right by a lot, right? And that's what gives difficulty to Lyapunov, to polynomials, because if there was a polynomial Lyapunov function, it better be that the value it takes here is less than the value it takes here, because the Lyapunov functions decrease along trajectories, right? But let's argue formally that this cannot happen. So the way we did it was we took a range of initial conditions on a line. So think of alpha to be 1 here. So this line could be k. I take k and I pick initial conditions here. And I look at the time they cross the y equal to 1 line. So the crossing would be here, 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 and here. So this you can compute where the crossing point would be. It would be e to the k to the minus 1. That's the x coordinate. Now, if you had any Lyapunov function, this should be satisfied. V at the end should be less than V at the beginning. And if V is a polynomial, this is impossible. Because if you plug in an exponential into a polynomial, the left-hand side would be an exponential function. The right-hand side would be a polynomial function. For large enough k, this would not hold. Okay? So that was simple, and it shows you that if you want to prove global stability, then you cannot do it with polynomials. But what if I just want to prove local stability, which actually, in most applications, that's the question of interest. In this example, there is definitely a local quadratic Lyapunov function, right? You can see that because the linearization of the system is minus x minus y. That's a Hurwitz system. You can see sort of x squared plus y squared is a Lyapunov function locally, right? And on compact sets, polynomials can approximate any continuous function arbitrarily well, right? So there's maybe hope that because we know there is a C1 Lyapunov function, maybe you can always approximate it by a polynomial one. Right? Okay. So that was actually a harder question which we finally answered last year or a year and a half ago with my student Bashir El-Gadir. So it turns out the answer to that is also no. And here's another concrete counterexample, which I like a lot. So this one is also on the plane, but it's degree 7. So what is the claim? The claim is that the system is again globally stable. All trajectories go to the origin. Here's that one trajectory following this. But now there is no Lyapunov function, no polynomial function even locally. So meaning that no matter what neighborhood you take around the origin, no matter how small it is, there will not be a polynomial Lyapunov function over that region. So no polynomial can satisfy the Lyapunov inequalities locally. So what's the intuition here? Okay, so first of all, how do you prove the system is stable? You asked me about rational Lyapunov function. This example happens to have a rational Lyapunov function. That's what proves that. And in fact, these green sets are level sets of W. Okay. Now, how do you prove that there is no polynomial? Okay. So let's just give names to this thing. Let's call this F0. That's the part of degree 5. And let's call it F1. That's the part of degree 7. Okay. Now, it turns out we could prove that what F0 does on its own, if F1 wasn't there, F0 produces periodic orbits, which actually exactly traverse the green dotted lines, which are the level sets of W. So if only the system was F0, its trajectories would go on the level sets of W and have periodic orbits. So F1 is drawing the trajectory in, that's why the system is stable. But as you can see, its degree is higher than F0 by 2. So as you get closer and closer to the origin, this part gets smaller and smaller because it has higher degree. And the behavior is more and more dominated by F0. That's why if you sort of follow this, you see that you're slowing down more and more and more when you go to the origin, because the behavior is closer and closer to being periodic, but there's always a tiny bit of push to the inside. Right? Okay, so now let's do this more formally. So suppose there was a polynomial Lyapunov function. In fact, we rule out something stronger. We rule out that there's not even an analytic Lyapunov function. But for my purposes, let's say this infinity is a finite sum. So if there was a polynomial Lyapunov function, so this pk is all the monomials it has of degree k, okay, then I claim that this inequality should be true. So because p is a Lyapunov function, p dot is less than 0, right? P dot is less than or equal to 0. And so what is pk0? So pk0 is the first non-zero term here, and f0 is the lowest order part of that. So how I'm going from here to here is the following. If a polynomial is always negative for all x, then its lowest order monomials should be negative on their own. Why? Because near the origin, only the lowest order monomials matter. If that term was positive, then near the origin, the entire polynomial would have gone positive, right? So that's where this follows. But I already told you that f0 has periodic orbits. That means that this quantity should actually be 0, because what is happening, let's say if I follow f0 and I evaluate this polynomial pk0. pk0 is some homogeneous polynomial of degree k0, right? And I know pk0 decreases. Well, if it ever strictly decreases, let's say the value starts at 5 and it goes to 4, well, what happens if the trajectory goes back? The value should be 5 again, but it went to 4 and is always decreasing. Does that make sense? So it cannot go back to 5. So the only way this can be true is that if it's identically 0, the value doesn't change. But what does that mean? That means that there is a polynomial, pk0, which is constant on the green level sets. But the green level sets were the level sets of a rational function. And then there is we prove algebraically that no polynomial can vanish on the level set of this function. So that's I think that's the end of the proof.
So now you ask the question, when they're rational, will they always be rational?
Yes, good. So that question is open right now. So let me be very clear what's open, because I'm going to talk about that. So the question whether there's always a local rational Lyapunov function is open. If you want it to be global, the answer is no, because on the same previous example, you can also prove there is no rational Lyapunov function.
So this example is not homogeneous, is it?
This is not homogeneous.
Right.
This is not homogeneous. So you can ask the question about homogeneous, which I'll do in a second. Both of my examples were not homogeneous. Okay. So that's a good question. You can ask, what happens if your system is homogeneous, which is what I'm going to do here, and then things get better. So, for instance, linear systems are homogeneous. There's always a degree 2 Lyapunov function. If you have a homogeneous vector field of higher degree, with the same student, we proved that there is always a rational Lyapunov function. So homogeneity helps you get a rational Lyapunov function, and moreover, we can prove that you can take its denominator to always be a power of sum of xi squared. Okay? Moreover, even though this is not a polynomial, you can find it numerically with the sum of squares and semi-definite programming technology. So what I said on the board carries through. There's an automated search for the coefficients of p to find this Lyapunov function. Okay? This generalizes the classical case. That case is when r is 0 and the degree of p is 2. Okay? I think I should better skip this proof. What am I going on to, Alexei?
Oh,
It's also
11:30.
maybe
You have about half an hour.
20 more minutes.
20 more minutes, yeah. I'll skip this proof to say something about this. But is this clear? So the short story is that if you add homogeneity, we can prove there is a rational Lyapunov function. We cannot prove if there is a polynomial one. That's open. Let me skip this proof. Then you may also ask, okay, you prove there's a rational Lyapunov function. Can you tell me is there a degree bound on the degree of p? What we can prove is that there cannot be a degree bound which only depends on the dimension of the vector field and the degree of the vector field. Right? So in the linear case, that's true. The degree bound is 2 period, no matter what this is. So here, there is no degree bound as a function of dimension and degree. It's possible that there's one that also is a function of the coefficients of the vector field. That I don't know. Okay. Okay, so maybe the last thing I want to say on this first half of the part is I want to just contrast rational and polynomial Lyapunov functions, which I found interesting. So essentially, this theorem is saying that rational Lyapunov functions can be arbitrarily better than polynomial ones. So what do I mean by that? So take any integer m, let's say m is 1,000,000. Okay. Then there are vector fields in fixed dimension and degree, in fact, in 2 variables and degree 5, such that you can prove their stability with the rational Lyapunov function of very low degree. So denominator degree is 2, numerator degree is 4. Right? But if you want to use polynomial Lyapunov functions, you need degree at least 1,000,000. And the m is arbitrary. Right? So in that sense, and in a sense, our literature mostly had looked at polynomial Lyapunov functions. So this suggests that maybe these rational Lyapunov functions deserve more attention. Moreover, to find this rational Lyapunov function is really no more expensive than finding a polynomial one. And the rough intuition for that is that the denominator is fixed. We don't need to search for it. We just need to put it there to allow more shapes than polynomials can handle. You still search just for the numerator.
What about R?
Yes, so whether R can be bounded, I don't know. So you see, I don't even know, for instance, whether you can always take R to be 0, which would mean that there is a polynomial Lyapunov function. It is possible that homogeneous vector fields have polynomial Lyapunov functions. I would think that's not true, but I don't know how to rule it out. Here I'm showing something less, that if there are polynomial Lyapunov functions, the degrees will be tremendously high, right? But we're not saying they don't exist. Okay. Any questions about the first part?
Have you ever tried to connect this to do you know Hartman-Gromman theorem?
No.
Which it gives you a conjugacy between near an equilibrium point, which is topological but not differentiable. And so if you look at the linearized equations, you could tell in some cases, without doing any work, that there couldn't be a Lyapunov function.
There could be a stable, yeah.
Yeah.
Okay, good question. So I don't know if this is exactly what you're talking about, and I haven't seen that, but there's some connection, partially at least, that I should have mentioned. So there is always a Lyapunov's linearization theorem. It says you have a nonlinear vector field, you can linearize it. If the linearization is asymptotically stable, then so is the nonlinear system. If the linearization is unstable, so it has a pole in the right half plane, then the nonlinear system is also unstable.
Yeah.
The tricky case is where the linearization has eigenvalues exactly on the what do you call this?
Why?
On the imaginary axis,
Yeah.
right? So pretty much that's where all the difficulty comes from. Even the Arnold conjecture, the reason it could be undecidable is exactly because of that, because otherwise those eigenvalues would determine the behavior, right? So because if anything that I presented, for instance, the what I constructed in the proof of NP hardness. If you go and check what the linearization of this would be, it would be in that intermediate case. Right? That's why the problem is hard. If you look at this counterexample, the linearization, actually you see the linearization is just 0, right? It carries no information, right? And one nice thing about homogeneous vector fields, why I think is valuable to have this theorem, is that Lyapunov's theorem, there's nothing special about degree 1. You don't need to just linearize the system. You can Taylor expand it to any order, right? If some lower order Taylor expansion is asymptotically stable, then the whole nonlinear dynamics is asymptotically stable, right? So what this allows you to do is, for some systems, the linear part can just be 0, but maybe the cubic part is asymptotically stable. And then if you prove that with the rational Lyapunov function, you know the entire system is asymptotic. So that's what I wrote here.
Yeah.
It's useful for local asymptotic stability of non-homogeneous systems because you can pick the lowest order homogeneous part. Right?
You also don't, and for a lot of applications for local
Yeah.
stability, you could just start out with an analytic vector field and then just say, okay, if I can prove the origin is asymptotically stable with a polynomial, then it's going to be probably asymptotically stable for the whole system. And I don't think you're.
You mean you start with the vector field and you?
To start with an analytic vector field, it's got an equilibrium point at the origin, and now just truncate it at some high level and
Yes.
then apply your ideas.
Right.
It seems to me if that's going to actually prove something locally for the original system.
Right.
Yeah.
That's what I'm saying. So, but the Taylor expansion would exactly do that.
Yeah.
If your function is analytic, you truncate it.
Yeah.
You are looking at the Taylor expansion of order m. If that's asymptotically stable, then the whole system will be right.
Locally, yeah.
Locally.
Yeah.
Yes. Absolutely. Yeah. Okay. So great questions, and let me move on to part 2, which I
have a question.
Yeah.
Your talk is very interesting. So
Yeah.
in the page maybe 13.
30. I'm not at 30 yet. 13.
13,
Sorry.
yeah.
Uh-huh.
And in this
Yeah.
example,
Yeah.
this example is not contain parameters here, right? So
No parameters.
Yeah, no
there.
parameters.
Well, the coefficients are 1.
Yeah. So I have a question. So if we consider a different system contain parameters, so is that possible? Yeah, we can determine the conditions on the parameters such that there exists a polynomial Lyapunov function.
Right. Good question. So you're asking, what if part of these coefficients are not fixed or unknown, and I want to choose them such that the resulting system is stable, right?
Right.
So that's exactly what I consider as a control version of this problem. So that's what was done in the robotics video. So the dynamics of this thing was not completely determined. Some of the coefficients are unknown, and you want to choose them to make it stable, right? So this technology can be carried through. Essentially, what changes is that you don't get semidefinite programs. You get what are called bilinear semidefinite programs. Essentially, people alternate between fixing the coefficients, looking for a Lyapunov function, and then fixing the Lyapunov function, updating the coefficients. That's what this does, right? And in each step, you minimize some measure of stability, roughly. Does that answer your question? So what you're asking has been studied. There are many papers on that, which is controller design with sum of squares methods, right? There's also other versions that have been studied with parameters. For instance, all sorts of robust stability questions. So for instance, you may have coefficients and you may ask, is it true that if these coefficients are between this and this, or are in certain polytopes in coefficient space, then for all values of the coefficients, the system is stable? This is a robust stability question, and that can be done also, right? So here I was genuinely looking at the simplest case where the vector field is given to you, you just want to test yes or no is it stable. Because the questions I was trying to answer, I think if we don't know the answer even in the simple setting, then there's no hope that we'll get. Yeah. Okay, so let's get to the second part, which I think is actually much easier to follow. For one, is in discrete time. Okay, so what is a robust to dynamics optimization problem, or what we call RDO for short, right? so the idea is simple. So suppose you have some optimization problem. You want to minimize some function f over a feasible set. Let's say the feasible set is omega. And in traditional optimization, if I want to minimize, let's say I want to go up as much as possible over this set, you know, the optimal solution would have been this extreme point here, right? So that's just like how an optimization problem works. But what you have in an argue is, in addition to f and omega, f is the objective function, omega is the feasible set, you have a dynamical system in the background, x star equal to g of x. Here I'm plotting it in continuous time because it's easier, but actually I'll talk about the discrete time case. Now what is the constraint? So you want to minimize f over the subset of omega that remains in omega for all time. So for instance, this point is no longer feasible because if you start here and run the dynamics, in the future the trajectory will go out and will no longer be feasible. So maybe the optimal solution would be somewhere here, because that's as high as possible I can go while remaining in omega for all time, right? So there's an invariance constraint that I want to impose, right? And this has many applications in different areas. Let me not mention that in the interest of time. So, but I think the problem should hopefully be very clear. So I have as input f and omega. That's my optimization problem. And the second part is a dynamical system, which I'm going to take it to be discrete. So G is a map from Rn to Rn. And then I want to optimize over the set of initial conditions in Rn such that not only the initial condition is feasible, but all its future trajectory is feasible. x1, x2, and so on. Okay? So this is not just one problem, it's a class of problem depending on what the dynamics G is. Is it linear, polynomial, whatever, uncertain, known, continuous, discrete, and what the optimization problem is, what f and omega are. Is it a linear program, quadratic program, and so on. Okay? So in this talk, I'm going to do the simplest case, which is my optimization problem is a linear program and my dynamics are linear. If there is time, I have a couple of slides on the more interesting dynamics where the dynamics switches between linear systems. So it's a time-varying linear system. So what is the simplest case? So this is what we call robust to linear dynamics linear program. So RLDLP for short. So what is a linear program? Is a problem of minimizing C transpose X over a polytope AX less than or equal to B. So the input to a linear program is A, B, and C. What is new here is this matrix G. G is n by n. So that's the linear dynamics. And I want to minimize C transpose X0 such that the future trajectory is always in this polytope. Okay. I don't need to actually talk about dynamical systems. I can just purely write this down as an optimization problem, which is infinite dimensional. It has an infinite number of constraints. I want to minimize C transpose X such that X is in the polytope, AGX is in the polytope, AG squared, AG cubed, and so on.
Excuse me.
Yeah.
When you write x sub k plus 1 equals gx sub k,
Yeah.
do you still mean k runs through
Over the
all
integers.
all integers?
Yes. Because 0, 1, 2. Yeah. Yeah. But again, this really maybe is. So that's the dynamics motivation, but this is really an optimization problem with a decision variable in Rn and an infinite number of constraints. Okay. So let's, throughout this talk, denote it feasible set by S. S is the set of points that for all powers of k, they remain in the polytope AX less than or equal to B. Okay. So let's do an example to see how this behaves. So here A and B define this polytope in R2. C is minus 1, 0, so if I want to minimize C transpose X, it's telling me to go to the right as much as possible. If there was no G and no dynamics, this would be the optimal solution. But now there is a dynamics, so if I apply G once, what happens is that all these purple points will leave the original polytope, so they're no longer feasible. I cannot consider them. This is the part that is left. If I apply G one more time, then another chunk leaves. These guys are not feasible. If I apply the third time, it turns out that no new point leaves. This takes some thought, but it is true that if this happens, then no point will ever leave in the future. The process terminates. And my final feasible set will be this new polytope. And the optimal solution will be here, is an extreme point that was generated in the process. It didn't exist at the beginning in the original polytope. Is it clear this example what happened? So I think this sort of suggests some natural questions. So first of all, if you want to get lower bounds on this optimization problem, is very clear what you should do. You should just truncate this, maybe run it to some 3, 4 something. If you drop constraints, the optimal value can only go down, and you get a lower bound because you're outer approximating the feasible set. Right? But the natural question is, does this phenomenon always happen? Does it always terminate in a finite number of steps? Will the feasible set always be a polyhedron? So if it terminates in a finite number of steps, it will be. If it is, how many facets will it have? And does that polyhedron have a tractable description? Right? You may also ask, how do I get upper bounds on this? Which is sort of more interesting because actually what I really want is a feasible solution, is an X that satisfies these constraints for all powers. Right? And a lower bound doesn't give me that.
Now,
Yeah.
now in the picture you
Yeah.
eventually got.
Yeah.
So that optimal point
Mhm.
is on a kind of a boundary.
Yes.
And what you do in this optimization problem is always numerical, is that right?
Yes. Yes.
So how do you know that your approximation goes on that side or on this side of that point?
Good question. Okay. So first of all, because this is a linear program, the optimal solution, there will always be an optimal solution at a vertex, which is a solution to a linear system. So you can actually write it down exactly over the rationals.
Okay.
Yes.
Okay.
So it is known that for a linear program, you can find a rational optimal solution in polytime, and you can actually certify its optimality. So that can be done. But if I'll tell you more when I write a semidefinite program. There are ways of formally ensuring that all the constraints are truly satisfied, right? But for a linear program, you don't even need to worry about it because the solution is rational, right?
But that's
Yeah.
if the coefficient...
If the coefficient is rational,
Oh,
absolutely.
right.
Like, all the input is rational. Yeah. Yes. Okay. So the first thing I want to say, so this was the feasible set, right? So it turns out this set is always convex, closed, and invariant. This first property is immediate, right? This is a polyhedron, is an infinite intersection of polyhedra. So invariant means that if I start in it and I apply G, I remain in it. That's also obvious from definition. Right? It is not always polyhedral. And it does not have a tractable description. So in the sense that...
Could that be empty?
It could definitely be empty sometimes.
Okay.
Yes, absolutely. Right. Just think of the situation where you have a stable G. So G is 1/2.
Right.
And your polyhedron is here. Everything will eventually leave and go to the origin.
Right.
That can happen. So it is NPR to check whether a point is in this set, whether a point stays in that, right? Which is the question. Yeah. Okay. So I only want to give you a proof of 2 because this can be done with a pretty picture. So here the original polytope is the unit disk. This is where I want to stay in. What is the map G? The map G is simply a rotation map. But rotation is by an irrational degree. Any irrational degree would work, right? So now if you think about it, what is the set of points that remain in the square for all time after they go through this rotation? Well, there is a unit disk inside that will certainly stay in it forever, right? Because if you start here, it will rotate. Now I claim that nothing else will remain because if you take any point, I wish I had a better, I don't have it. So let's say the unit disk is here. If you take any point outside, it's gonna keep rotating. And you can show that because the rotation is irrational, for some number of rotations, this will go out because if you start outside the unit circle, you'll have a bigger unit circle which leaves the square, right? If you draw the unit circle which is slightly bigger. So there will be a part of it outside. Let's say this tiny part. And because the rotation is irrational, that part will be visited infinitely often, in fact. So you will step outside. Okay? So this is an example where you started with everything rational and polyhedron, you ended up with a convex set which is not polyhedral. So that can happen. So more formally, we analyzed what happens to this sequence of outer approximations. So S is the true feasible set, SR is a truncated version. So you can think of it as a set of points that remain feasible up to R steps. So they don't leave the polytope up to R applications of the map G, right? So the first one is just the polytope. Then they get tighter and tighter and they asymptotically converge to S, right? And one question you want to ask is, when is this convergence finite? Like my example. So that we completely characterized. So the convergence cannot be finite only if one of these three situations happens. One is if the spectral radius of G is more than or equal to 1. So that's actually the example we had here. So what's the spectral radius of this matrix? Is exactly 1. It's a rotation matrix. One is if the origin is on the boundary of the polytope, and one is if the polytope is not bounded. So let's not worry about this, but there are 3 concrete counterexamples where convergence is not finite. This is the one where the origin is on the boundary, and it takes an infinite number of steps to the final set S is this lower dimensional half line. And here is one where the polytope is unbounded, and as you apply G more and more, you get more and more cuts which never stop, and they take care about the shape. Okay. But the main theorem is this. So essentially, if you rule out these 3 bad cases, so if rho is strictly less than 1, the polytope is bounded and contains the origin in its interior. So this is literally saying remove the 3 cases, right? Then convergence is finite. Not only is finite, but we can compute how many steps it will take. It will take a number of steps, which depends polynomially on the size of the input data. Okay. I think I'll give you an idea of this proof when I stop. I think that's the best. So the idea of this proof is the following. So this, let's say the red is my original polytope. Okay. Because the spectral radius is less than 1, that means the linear system xk plus 1 equals g times xk is asymptotically stable. It's taking all the points to the origin. So we know from classical control theory that if that happens, there's always a quadratic Lyapunov function. So that's actually something I mentioned. So the ellipsoid I'm plotting here is a sub-level set of that quadratic Lyapunov function. So if you start in this ellipse, you apply G, you remain in the ellipse. In fact, the ellipse will shrink after each application of G. So then you compute a level set of the quadratic function for which this level set is completely outside the polytope. And you do another one which is completely inside the polytope. Okay. And then you can compute how many steps will it take for this ellipse to shrink and be inside this small ellipse. Right? So let's say that number of steps is 100. After 100 applications of G, any point in the big ellipse will be in the smaller ellipse. Right? I claim that's an upper bound on how many steps you should worry about for points leaving the red set. Why? Because after 100 steps, every point in the red set is here. Because even every point in the bigger set was going to end up here. Right? Once you're there, you never leave this set. This is an invariant set. So if you're in the red set and if you want to leave it, you better leave it before step 100, because at that point you're here and that's too late. You're going to be here. Right? So, then the hard part of the proof is to compute how many steps it takes for this happen. And for that, you really need to do a numerical analysis of how large the sizes get. So first of all, you need to compute this ellipsoid. So the matrix P is a symmetric matrix that defines the ellipsoid. So it's a set of points where x transpose px is less than 1. You need to compute the shrinkage factor. How much does this ellipsoid shrink after each application of G? And you need to compute these 2 numbers, alpha 2 and alpha 1. These are the level set numbers that put the bigger ellipsoid outside the polytope and the smaller ellipsoid inside the polytope. Once you have all this, you can compute how many steps it would take. Okay, let me stop here. I'm sorry I went over time. Okay.
Additional questions?
What's the time to solve a typical real problem?
I guess what you mean by real. I'm not a very real problem person, to be very honest.
I mean, let's say robots.
So, but a problem of so something like this you can solve even in like thousands of variables because it's a linear program in the order of seconds very easily. So the robot problem, actually there's a long history behind the robot problem that I did not mention. Okay, let's go back to it. So what I present to you, so this talk I tried to emphasize the dynamics aspect, right? I actually can see the interest in optimization, which I appreciate a lot, but I did not know, right? So I did not talk to you about how sum of squares optimization works, right? I sort of roughly went on the board to say there's a semi-definite program. So semi-definite programs are not the most scalable class of optimization problems. They do scale, but for this type of control problems, most of the literature has vector fields with up to roughly 10 variables, or maybe 8 to 12, depending on their structure. No. So I did a lot of work, maybe 4 or 5 years ago, on making STP more scalable, and I've given a lot.
Scalable?
Sorry.
What do you mean by scalable?
Okay, so essentially, I mean that in a practical sense. So essentially, we produce algorithms that improve running time by a square factor. So essentially, they take a square root of the old one, and those algorithms are actually what was used to solve this. So I lied a little bit. This is not standard semi-definite programming. If you're interested, I have a paper which is also is for a very broad audience. It's called the DSOS and SDSOS optimization. This is with Ani Majumdar. So these are alternatives to sum of squares, which are more conservative. So what that means is that they would give you smaller regions of attraction here, but they're much faster.
Alternatives to sum of squares. What do you mean by that?
Yeah. So I mean that they're so sum of squares is this thing that I roughly described on the board, right? So what they do is that the way sum of squares proves a polynomial is non-negative, it proves it that it's a sum of squares of other polynomials, right?
Mm-hmm.
The way these techniques do, they prove that the polynomial is non-negative by doing the same thing, but they restrict the structure of Q. So Q is not any polynomial, it's some structured polynomial.
Mm-hmm.
So if you want, if I were to draw a picture in coefficient space, let's say this is the fixed n to be 5, you have 5 variables and you have degree 4. So in coefficient space, there is a convex set. This is all polynomials that are non-negative. Non-negative polynomials.
Mm-hmm.
So these are all the coefficients. And this is a convex set because if you take 2 non-negative polynomials, you average their coefficients, you get another non-negative polynomial. So inside of this are the sums of squares. So this is the SOS set. Okay. So ideally, in all these applications of dynamical systems, you want to optimize over the big set, over the non-negative polynomials. You want a Lyapunov function to belong in the set. Right? But that set is hard to optimize over. It's formally NP-hard. So you give that up. Instead, you search over the SOS, and at least this is tractable in the sense of theoretical computer science, is polynomial time. You can solve a semi-definite program, and this can be done in polynomial time, which you ask me what do I mean by efficient. If I'm a theoretician, that's efficient. If I'm a practical person, well, it's a question whether it is or not, right? So what we did in this paper with DSOS and SDSOS is to go even further. So we have 2 more sets that we defined. One is called the DSOS set, which is always polyhedral. And the reason it's faster is because it's actually a linear program, search over it. And there's an intermediate set, which is called SDSOS, and this is not a linear program, it's what's called a second order cone program, which is exactly intermediate between linear and semi-definite, still much faster than semi-definite, right? So that intermediate one is what stabilizes this robot in this picture. And if you go to that paper, there's an explanation of that. There's a separate paper by Rosted, Drake, and Ani Majumdar. So he's a roboticist at MIT, Ani is at Princeton, where it's just about that and how this was done.
So 30 states means 30 variables?
30 variables.
And in your
Yeah.
complexity, n plus d.
Good. So actually, so the most expensive constraint in this robotics example is to make sure that the derivative of the Lyapunov function is positive. Usually that's the highest order thing because the degree is usually higher than the degree of v, because minus grad v is minus the gradient of v times f. So in that robotic example, f is cubic. So f is a Taylor expansion of order 3 of the true system, which is a mix of polynomials and trig terms. Right? And v is quadratic. V is degree of v is 2. That means that the degree of v dot is 4. Because degree of the gradient of v is 1 and f is cubic. Right? So the problem we had to face is to make sure that a polynomial in 30 variables and in degree 4 is positive. That's what we had to do. We had to search for that, right? So the size of this matrix now, so n is 30, d is half of that, d is 2. So this is roughly n to the d, this number. What is 30 squared?
1,000, about 1,000.
This is about 1,000 by 1,000, right? So that is beyond what an STP solver can handle right now, right? But these techniques could easily handle it. The running time of that robot was like a minute. Or two.
Very nice.
Thank you.
So if you're talking about robots and,
Yeah.
Some local neighborhood
Mhm.
of the system where it becomes stable, but in the original formulating of this problem,
Yeah.
do you include constraints?
In the original, like safety constraints for the robot and so on.
Yeah, right.
In this example, no, it was not done. But
So
But there-
you could solve the problem that is way outside your constraint.
what do you mean? Okay. So
I mean-
you mean like?
Physical space constraint and other things.
Yeah. Okay. Actually, now that I think about this, we had in this paper control constraints. That as I told you, some of the coefficients are unknown for you to choose.
So
Right?
let's put it the
Yeah.
other way. Instead of equations, can you have inequalities?
Which equations?
I mean, when you state the problem, right?
Right. So yes, the answer is. So I just want to understand if by constraint you mean state constraints or control constraints. But it doesn't matter because
It
both
doesn't matter, right?
both of them can be done. So in this example, what we imposed was control constraints. So we ensured that the control variables are in a certain set.
Right.
And that set, it just needs to be a basic semialgebraic set.
Okay.
So it needs to be defined, the constraint set needs to be defined by polynomial inequalities. If that's the case, then yes. And if you have sort of physical...
So you can do the control because you can put you can take care of the constraint because you're looking for the parameters.
Yes,
But
subject...
what about
Yeah.
but what about the space variables?
What about state constraints?
State
Yes,
constraints.
yes. So you can do that. There was no state constraints as far as I remember here.
Right.
But it can be done, and because it's an important problem, right? So for instance, you want to have collision avoidance constraints.
Right.
Right? So suppose you want to say that if this is my state space, and if I start in set A, I want to make sure that the system will never go to set B. This is an unsafe set.
Right.
Right? So I want to show, no matter where I start here, I want to make sure trajectories don't go there, right? So this entire thing actually carries over very nicely. So what I have to do is to find the function v with the following properties, for instance, that v on A is negative. So by that I mean v of x is negative for all x in A. V on B is positive. And there's an underlying dynamical system going on. Right? And V decreases again. So V dot of x, which is grad V f, is less than or equal to 0. So if you find the function V that satisfies these constraints, then I claim that your system is quote unquote safe in the sense that trajectories from A don't go to B. Why is that? Because if I start anywhere here, I don't care where it is, V is taking a negative value, right? Then the trajectory will do something, but V on that is always decreasing, right? So you can never end up in B where V was positive,
Right.
right? So these three inequalities give you a proof of collision avoidance, right? And then you can parameterize V as a polynomial, so B of x can be sum of C alpha x B alpha. This is a monomial notation. And the task of finding these coefficients, subject to the constraint that these three inequalities hold, will be again a sum of squares program.
Okay.
If you're interested, actually, there's a paper by by people at UPenn who did exactly that.
Thanks.
More questions? Okay, that's it. Thank you.
Yeah.